did the week 1 raw notes. Or maybe someone did, but they didn't put this link at the bottom. Let's go for all. We'll look at all. Go back to here. See if we can find them. Okay, here are some people. So Merwin's done some, and Merwin wrote some expanded notes too, which are really cool. And Ramara did some. Lots of people did them, so that's really cool. And if you click on those, these are the people whose job it was last week, 16 people, to write down everything that happened in one of the lectures. So if you drifted off during the lecture, you could go and look at their raw notes and you'll see what happened in the lecture. They don't put any expansion stuff in here, they don't add extra features, they don't put their own ideas in, they don't do further work, because this is just a recording of what happened in the lecture, so we know what happened in the lecture. If they want to do extra stuff, then they put it in the expanded area. Yeah, they just write an elaboration. And one student did that, I think it was Merwin again. Merwin wrote some expanded notes and they were cool. Well done. Who's Merwin? Wave your hand. Yeah, well done. Cool. That was really good. So here's the OR gate. He sort of put in a truth table and he explained about it, and he gave another way of creating an OR gate using resistors, and he did all sorts of stuff. Now it's expanded, which means you don't have to read any of it, and none of it's examinable, and none of it's accessible, and you can completely ignore it. But if you're interested, you could go and read it and learn some really interesting stuff. Does that make sense? So that's what those notes are for. Yes?
Correction, I did not do the expanded notes. The extra logic gates were done by Robert.
Oh, okay, someone else did it, and they put them on your page. Yeah. And then I ultimately edited your page so only you could edit it. Because of course, when you're writing notes yourself, and I'll show you how to do that during the labs this week, you should set it up so no one else adds to your page. If someone else wants to add some notes, don't put them on Merwin's page, put them on your own page. Make your own page to do it. And if you don't know how to do it, ask your lab guy how to do it. It's very, very easy how to do. Okay, was there a hand waving? I just wanted to make clear that when I was talking about the nice notes before, I wasn't actually talking about the people who'd done the raw notes. All these notes, notes, notes. Very confusing, isn't it? Okay. Well done. And well done to Robert or whoever it was that did the expanded notes there. They're awesomely good. Okay, so let's go back to the schedule. Where is it? Hiding around here. And let's look at today's lecture notes. And let's look at Richard's notes. Who's doing it? Expressions. I haven't done expressions. I'm about to do them, but we got distracted. Simple programs I've done. Human error I wanted to talk about, and the Viking 2. I didn't get to talk about human error and Viking 2, so let me just talk about that quickly. You will find that when we're running programs, we are our own worst enemy. And the reason that we're going to have mistakes in our programs and our programs aren't going to work is not going to be because of some external thing. It's going to be because we've stuffed up in some way. And we're human, and no matter how good we are, we stuff up all the time. Me especially stuffs up all the time. It's just part of being human to completely stuff up. And one amusing example I thought of I'd give that, since we've sort of got a Viking theme to today's lecture, because we've already mentioned them twice, is the Viking 2, which is that incredibly expensive program that NASA had to put a landing robot on the moon. Does everyone remember that? A long time ago, before they gave up on Mars and doing any work at all on anything except the space station. They put a robot on Mars, and it was awesome. And they put down 2 robots on Mars, and they were driving around for a long time, and they were doing really well and gathering all sorts of really excellent data. And we had a little really tenuous radio connection with them. And we could reprogram them remotely if we needed to adjust their programs. Only when their aerial was pointing exactly at our aerial, and only at certain times of the day, and when they switched on, and they didn't have much power. But occasionally we could beam signals at them saying, oh, modify your program to do this and this. It's like a Windows program downloading patches. So the Vikings were wandering around for a long time, and then people noticed that the Viking 1 failed, and people noticed that robot failed. It was something to do with its battery, people thought. It might not have been charging right, or the batteries were getting old, or there's something funny. And someone really clever thought, hey, if we just change the battery charging program slightly, we might be able to get more battery life out of the remaining robot. So they wrote a modified program to change how the battery charged. Now it's getting exciting. Wave at me when it starts to get exciting. And they thought, so we've got this thing and it costs us like $100 billion zillion to get it up there, and we'll never get another one there again. And I know I'm going to fool around with its program because I thought of a way of improving it. So you should all be waving now. It's like mechanical engineering students when you say, so I went into the elevator, and they all start going, They all use the lifts. They all walk down the stairs. I mean, yeah, okay. So here's someone, and they're going to fool around with a computer program to make things better. So what they did was they wrote a new program to do the battery charging, and they uploaded it, but they stored it accidentally, human error, when they were typing it in. Oh, send it now. Now, oops. They stored it in the wrong spot. They stored it so it overwrote the program that told the radar where to point, the radio dish where to point to pick up radio signals. And they went, oh, I shouldn't have done that. Where's the undo button? And then they spent a year trying to re-establish contact with it. they worked out where it might be pointing now, and by coincidence, where it might be pointing now occasionally would point to Earth for about 3 seconds. It would go whoosh across Earth as Mars spun around. And they'd go, in those 3 seconds, it'd be in the middle of the Atlantic going, we've got 12 seconds now while the radar dish might be pointing to us. Upload a new program now. And they never, ever managed to restore contact with it. It was lost completely because some klutz just stored it in the wrong spot. They typed a 6 rather than a 60, something like that. Human error will kill us every time. It wasn't the physics, it wasn't the money spent, it wasn't the engineering, it wasn't anything else. It was some person accidentally typing the wrong number in when they uploaded it. Very, very sad. By the way, with all the photos we've taken of Mars, with all the flyby missions, we've actually taken photos of it, and we can see it sitting there. Aerial's still up in the air, just waiting to hear from us. Yeah, the Viking 2. Goodbye, Viking. Okay, chips, computer chips. We did the 4917 chip last week, and we looked at how to program it. And then in your labs, we asked you all to think about it and think of a way we could improve it, because we found we had a very small budget to improve it. And electrical engineering at some other uni, which one was it? UTS, are also doing a 4-bit chip, and they're starting to get a bit more market share than us. And we thought, let's improve our chip so we steal it back. And so, of course, our market is students and teaching them how to program. So how could we make it more appealing to students? So you guys all got together and thought and brainstormed in your tutes how we could improve this chip to make it a more pleasant thing to program, how we can make it more powerful. There was a lot of debate, and the tutors have reported back to me that more or less the general consensus seems to be that 4 bits wasn't enough. Would everyone agree with that? It was very annoying. You could only store numbers up to 15, 0 to 15. That wasn't enough to do any serious calculations. You couldn't print letters out properly because there weren't even enough codes to represent all the letters in the alphabet. The alphabet has more than 16 different letters in it. So we could only print numbers, and it was just very annoying. So we took a vote on it, the tutors and I, and we decided we will expand it, and we've done a new design over the weekend for an 8-bit chip, which is exactly the same as the 4-bit chip, except now you can store numbers between 0 and 255. Okay, so it's pretty cool. Yes? You're waiting, it's getting exciting now. It's just getting more and more exciting. After you wave your hands, there's nowhere to go, is there? I guess you can start jumping up and down. Oh. Yes?
Can you give it a bigger bell?
We give it a bigger bell. We didn't think of that. Well, we had some engineering constraints. There were lots of other good ideas. A bigger bell was a great idea. Did you suggest that to your tutor? Because I didn't pass that on. No, you should have suggested that. We had a whole lot of other suggestions of ways to improve it, but we only had enough money to improve it in one way. So you guys are going to get the new chip this week and some exercises to do on it in your labs. At the end of the week, or during your tutor's going to ask you, what annoys you the most about this chip? How could you make it better or more useful to do more useful things? And this time I want each tut to write actually a short, just like a paragraph or two, explanation of what their proposal is for improving it and the reasons for it. And we're going to throw it open to a big vote to everyone this time about how we're going to improve it for the next version of the chip that will come out in a few weeks' time. Okay? And we're going to keep on improving this chip. And by the end, I'm hoping we're going to have an Intel equivalent, and we'll control the world, and that'll be great. So well done to that. Now, solving problems. Let's just go back to writing programs for a sec before we look at solving problems. All right, so here's our very simple program we've written so far. It had % in it and it had 2 in it. Now I'm going to just kill the GST rounding error thing. In fact, let me save that as another name. W2 GST, I'll call that. And then now let's get out of here and let's load the old version. Okay, so now we've got a copy of it saved under a different name. I'm going to kill this GST thing. How many? And we're just going to have dollars, and we're going to get 2 other things in, maybe int cents. And how many dollars do you have? And let's also do how many cents do you have? So we're reading in dollars and cents. And now let's do some operations. I just want to show you the sorts of things you can do. We've got 2 numbers. How could we combine them? Yeah, let's call it output. Int output. So we've got something called output. So I'm going to make an output number. Output equals, I could say dollars plus cents. Now that's crazy. That'd be cool, wouldn't it? If you could add your cents and count them as dollars. So if you had $50 and 50 cents, you add it together, you get 100. That's pretty cool. So that's how I add them together using the plus. How do I multiply them? What if I wanted to calculate dollars times cents? You wanted to sort of calculate the area of your wallet in some way. times. Yeah, it's that star symbol. You can put spaces between if that looks clearer. If I wanted to, we've done divide. If I wanted to divide my dollars by cents, slash, what have I done? Plus, minus, times, divide. Oh, I didn't do minus. Minus is, okay, so we can do all these basic operations. What if we wanted to do something fancy, like dollars minus cents times 6? Can I do this? Dollars minus cents times 6. Yes, no. Who thinks yes? Who thinks no? Who has no idea? Okay, you guys got to commit to something. Well, if I stuck in 10, 5, what's the answer going to be? It could be 10 minus 5, which is 5 times 6, which is 30. Or it could be 5 times 6, which is 30. Did I say that something was 30 that wasn't? No, 5 times 6 is 30. Yeah, that's right. 10 minus 30 is minus 20. The answer could be one or it could be the other. Which one is it? You might think the answer is... No. Answers involving actual numbers are wrong. Okay? You might think the answer is... try it out, and that's not a bad answer. But an even better answer is... who cares? Who cares? It's going to be one of those two things, and if we knew the rules of C really intricately, we'd be able to predict which one it was. But both of them are sort of plausible. As a programmer, you're skirting around the edge of human error all the time. You don't want to write a program that works only if you know intricate rules about how C works. That's confusing. Because if you made a mistake and guessed it was going to be one and it was the other, and this code went through and you wrote this code, and it turned out that it was the other, you'll never find that bug because you'll look through it a million times and you'll always read that the way you want to read it. So we could be optimistic or wistful about how C might work. We could look it up in the book about how C would work. But to all of those things I say, who cares? I don't even care how C works. I'm pretty sure C probably does it the right way and does the multiplication first, but I don't care. And if I ever wrote a program that relied on C getting that right, I'd be writing a shonky program. What should I do? Put in brackets. Yeah, brackets. Anything that's ambiguous is a disaster waiting to happen. You might be clever enough to know how the ambiguity is going to be resolved, and you might be correct. Or you might not. Never have ambiguity. Ambiguity is bad. No, let me rephrase that. You know which way it's going to be resolved, and you will be correct because you're really smart. But one day someone else will write a program doing this, and they'll get it wrong. Does that make you feel better? I tell you, I would get it wrong. Okay, so if I want it to be this way, I'm going to do that. And if I want it to be the other way, I'm going to do that. And I don't want to see you guys writing any ambiguous code. And I know it's not strictly ambiguous because there are rules about how to disambiguate it, but I don't care. Write it like that or like that. Does that make sense? Okay, so you've seen now this is a more complex expression. Dollars minus cents times 6. Let's run it and see how it goes. Are we even going to find out how it would have gone without the brackets? No, I'm not going to find out. I'm not going to find out ever. Never going to find out. No, because that way is the way of saying, you try it when you get home. Just don't tell me you tried it. But that way is the way of tolerating ambiguity, and we just don't ever want to have it. What's happening? Saying here, GST rounding error. An undeclared. What is undeclared? Remember I said the word declare and then the word initialize? What does declare mean? When you create it initially and you say it's an int or whatever it is, and it's saying it's undeclared, which means someone mustn't have said, the program must refer to something called GST rounding error, and no one said whether it's an int or whatever. So where is it? Here. I'll just kill the offending reference rather than define it because I don't want GST rounding error in my program. Oh, output's not defined either? Oh, I don't use output? That's okay. I don't mind using output yet. Okay. Oh, yeah, so we'll never see what the answer is. Here we go. Dollars equals %D. Cents equals %D. Output equals %D. How does that look? And then down here we say dollars, cents, output. Okay, so it's going to print dollars equals %D, that'll be the first one. Dollars equals the value of dollars, cents equals the value of cents, output equals the value of output. Let's compile it and run it. And I'll make this compiling window a bit smaller, so it's possible that you might even be able to see the program at the same time. Oop. Yeah, look, you can see some of the program at the same time. Okay, let's go. Compile it, run it. How many dollars do you have? I have $23. How many cents do you have? I have 24 cents. How can I have 24 cents? I have some 1 and 2 cent pieces at home, and I'm saving them up. And one day I'm going to use them. I'm going to hand them out as a prize. Yes. Okay, is everyone cool with that? Output equals -6, is that what we expected? Dollars minus cents is 1 times 6, sorry, is -1 times 6 is -6. All right, so is everyone cool? So that's how we make simple expressions. You've seen arithmetic expressions using plus, minus, divides. You can make them elaborate and as complex as you want. Now, let's jump back to solving problems. Given a problem, how do I solve a problem? Because we're about to get task 1, your first task. I'm actually going to release the draft today, but the official spec isn't going to come out till Thursday or Friday. Can't remember which. It's normally Friday, but maybe we bring it out a bit early because of Anzac. Easter. You're going to see it, and here's what you're going to think. So if you've already programmed before, you're going to look at task 1, and you think, oh, that's very straightforward, and you'll knock it over in a couple of days. And you'll notice that I think if you've already programmed before, you should be able to do task 1 in 1 day or 2 days, or maybe even 3 days, but probably 1 and maybe 2. So the due date for task 1, if you've already programmed before, is very early. It's before the end of the holidays. The due date for task 1, if you haven't programmed before, is the end of the first week after the holidays. So you can ask more questions and you tutor after the holidays and things like that. But you should certainly start working on it. We're releasing it early so you work on it over the holidays. How do we know if you've programmed before or not? We don't. And we don't care. You work it out yourself. There's no reward for handing it in early, but just as a personal goal to set yourself, if you've already programmed, I expect you should be handing it in a couple of days. And if you haven't programmed, I expect it'll take you about 10 days to do. But yeah, hand it in whenever you want, of course. Now, when you see it, especially if you haven't programmed before, you're going to look at it and think, okay, that's a problem. I can solve that problem in my head. As a human being, I know how to solve that problem. But how do I write a program to do it? How very annoying. And you'll sit down in front of the keyboard for a long time going, I can do it. Why can't I tell the computer how to do it? And you'll keep saying that over and over again. And you'll be relaxed and happy to know, hopefully, that this is what every other programmer in the history of programming has gone through when they've sat down to write their first program. You think, that's funny, I know all the bits. I know how if works and printing and plus and minus, and that's all this assignment involves. If, printing, plus and minus, and percent and divide and those things. It doesn't involve anything else except those. I know all those bits, I know how they work, and I know how to put them together. And I know the problem, and I understand the problem, and I can solve the problem myself if you give me pen and paper. Why can't I use those bits to solve the problem? Does anyone have a thought as to why you can't? Why it seems really hard when you first try and write a program? Why it's difficult? Yes, is that a hand up? Is that just a stretch? Yeah.
You don't know the syntax?
You don't know? They will know enough of the syntax. No, syntax is just the rules of the language. So like putting a semicolon in and how to use plus and minus. No, all the syntax that we've taught you, all the rules of C we taught you in the first couple of weeks, up till now, in fact, you now know enough to do the first assignment. You need to know nothing more than that. Yeah. Thinking algorithmically. Yeah, what does that mean? Say it in different words in case people don't know what algorithmically means.
It's the processes you need to type in order to solve problems.
Yeah, the processes you need to take in order to solve problems. How to convert this ephemeral, wishy-washy thing you do in your head that lets you solve it because you're really smart when you solve it yourself, how to convert that into precise rules. It's a sort of a self-reflection exercise. You can do it, you have to observe yourself doing it and think, well, what am I doing when I do that? What am I doing? How did I solve that? And you have to really look closely at yourself, and things you take for granted, you'll have to think, oh, I really did that, then that, then that. Oh, wow. So it's going to be quite weird. For a while, you're going to have to break things into really small steps. And although the steps all make sense, sometimes it's hard to see where to go from a big problem into the many small steps that solve it. So I'm going to give you some tips now about how to go through this process, which we call problem solving, which appears in all disciplines. There are general ways that people have come up with for how to solve problems. So I thought I'd give you a few tips each lecture. The first tip is top-down versus bottom-up. There are generally two ways of approaching a problem in any field, not just in computing, in any field. One's called bottom-up. And bottom up is you get all the bits you need and you assemble them into larger bits. And you get those bits and you assemble them into still larger bits. And you get those bits and you assemble them into still larger bits. And you keep assembling bits until finally you put the bits together to make the very big thing you wanted. And that's called bottom up, because you start with the small bits and you're working towards this lofty big goal. Does that make sense? That's the natural human way to start solving problems. But that way actually isn't a very good way of solving problems. Because you'll tend to build a whole lot of components along the way that when you get to the end you find you won't need, or they won't do exactly what you want. And you'll suddenly go, oh, I've built all these things, but I still can't solve the problem. The other way of solving problems is called top-down. And this is a really important way of solving problems that applies to lots of discipline. In a top-down approach, you start with the big problem and you don't worry about the details. It's a very manana, like tomorrow, man, relax, it's okay. So it's this very cool, laid-back way of programming or solving any problem. So you go, all right, I need to take over the world. So you can say, all right, I'm going to start teaching you about explosives, and I'm going to start teaching you about Microsoft, and I'm going to start teaching you about Macquarie Bank, and okay, and then I'll assemble them, and I'll do that, and I'll make friends with this guy, and okay, you get all the bits, and you're constantly thinking, how can I put all my minions together to do it? That's bottom up. Top down is you think, all right, conquer the world. Step 1, conquer Australia. Step 2, conquer America. Step 3, conquer everywhere else. Right, so I've got a 3-step plan. That's top down. And then someone says to you, how do you conquer Australia? What do you say? Tomorrow, what about that tomorrow? And you just relax. So you go, I've finished my program now. Conquering the world is conquer Australia, conquer America, conquer the rest of the world, finished. Relax. And you go out and you have a Sunday and you have a nice happy time and you watch a movie. And you come back and then the next day you say, all right, now I've got 3 problems to solve, but what's the nice thing about these 3 problems? They're smaller. They're smaller problems. Conquer Australia. How can you conquer Australia? Someone have an idea. How could you conquer Australia? You could start a union? I don't think unions are going to conquer anything. They conquer themselves. Yeah? State by state? Oh, I like the way you're thinking. We're going to do it geographically. Okay. And then eventually it's conquer this chair. Oh, I got this chair and that chair and that. Okay. Okay, yeah, so we could do it state by state. There's nothing wrong with state by state. That's a cool way of doing it. But let's, just to make it a really compelling example, let's think of another way of breaking the problem down other than geographically for the second cut. Take over the military. Take over the military. Yep.
Run stuff and leave it for later.
Right, yeah, leave it for later. Yeah. No, we have to actually do something today. We have to break it into 2 bits. We can't just say, oh, to conquer Australia, I have to conquer Australia. Now I can have another Sunday. That's slack. No, you can only relax when you've broken it into 2 smaller problems that put together clearly would solve the big problem. And each of them is smaller. So you think, all right, conquering Australia, maybe I can do it in a military sense. I was thinking maybe more you could just do it in a, well, okay, let's do it in a military sense. Thank heavens we're not recording this, because under the, what is it? Sedition Act or some law, yeah, I'm encouraging you guys potentially to take over Australia, could be arrested. So I'm very sorry. So yeah, you want to take it over the military. All right, so suppose we say take over the military and then using the military, take over Macquarie Bank. And once we've got the military and Macquarie Bank, we control everything. Okay. So I think, all right, now how do I, so then I relax. All right, so I've broken this into, why don't I use a real chalk rather than finger chalk? So to take over the whole world, take over Australia, take over America, take over everywhere else. Take over Australia is take over the military, take over Macquarie Bank, and some sort of tidying up process. How do I take over the military? No, I relax. I can go home. Now I can have a Sunday and watch another movie and do all sorts of fun. Come along on day 3. How am I going to take over the military? Okay, now you do some sort of crazy thing like you see in movies, and so on and so on and so on. But the idea is, with a top-down design, you're trying to fight your enemy. And your enemy in coming up with a good design is yourself. Your brain is always going to freak out and go, I can't do it, I can't do it. It's like writer's block. You'll get problem solver's block. You'll just freak yourself out. It'll seem too scary. You don't want to give up. You have to keep persevering. So the idea is you sort of do it psychologically. You break it into smaller tasks, and if they're still too daunting, you break them into smaller tasks. And if they're still too daunting, you break them into smaller tasks. And you keep doing this breakup until finally you get to tasks that are really small, like, I have to open the door. Oh, I can do that. I have to, get on a bus. I can do that. I have to mix fertilizer with, no. But, okay, so, you see, you break it into a series of small steps. Each one you can do. Then you can solve the problem. So you're fighting yourself. Otherwise, you're going to freak out completely. If you were a complete uber genius guru, you could do it bottom up. You could assemble all the bits like MacGyver does. Yeah, he gets all the little bits first, and he puts them together and solves a big elaborate problem. But the problem is with bottom-up, you can only solve problems up to a certain size. If you're really smart, up to this big. If you're a complete genius, up to this big. If you're the smartest genius ever that lived, ever, up to this big. But you still can't do a problem that's this big. With top-down, you can solve any size problem, and it doesn't strain your brain as much. So my constant suggestion to you guys is, when you see a big problem, don't freak out. Think about it and be relaxed and happy and calm, because freaking out is your enemy, and break it into small steps. Now, when I introduce the task, I'll suggest the way you might want to break it into steps to start with. How are we going for time? Oh, yeah, we've got heaps of time. The last, strategy number 2 for solving problems is this. As you do each thing, test it to check it's right. And keep track of the tests you've done. You're going to have to be systematic here, like a scientist. You're going to keep like a lab book. And every time you change or improve, you're going to add more tests to your bank of tests. And you're going to retest it against all your tests. So you're going to start off by saying, maybe I have to write a program which can listen to a piece of music and rate how good it is. That's an elaborate piece of software. So first of all, you think, OK, I'll get it to listen to rap music and rate how good that is. And you get that working and you test it 0, yes, 0, yes, 0, yes. OK, it's working. Then you think, OK, I'll get it to test like just all music that Eminem's ever written. And then, it's not that funny. OK, so you just keep going wider and wider, wider and wider. And every time you add more features to it, you think, OK, now I'll get it to test all music coming from the Northern Hemisphere. And every time you add new features, you run your old tests against it as well as your new tests, and you're constantly adding tests. You keep track of all your tests, so whenever you're stuck or things don't work, you can look over your tests and say, oh, I tested that and that works, I tested that and that works. Instead of just, oh, it doesn't work, it's, oh, it doesn't work and it's this precise problem that's causing it. So test everything and keep a track of all your tests. OK, we're going to talk a lot about testing in the course, so let me just now say that's a general introduction to testing. Each week we're going to talk a little bit more about testing, because it turns out in writing a computer program, a lot of the trick is getting your testing right. Or it can be. All right, let's go back to functions now. Where are we? Oh, does anyone have a question? Yes?
When you're working from the top of the...
Yep, hang on, let me put the lights on. I've forgotten your name, but I should know it. Tom. Sorry, Tom.
When you're working from the top down view,
yes.
The testing, if you split everything into groups,
yes.
and you'd make one thing at the very end of the tree at the top,
yes.
then doesn't that mean you wouldn't really be able to test it because you wouldn't be able to test it?
OK, Tom's got a good question. If you're going to be making stuff and you're breaking it down, 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 are you saying when you finally get to one little tiny little detail here, how are you going to test this one little thing?
Yeah.
That's a really good question. So you see, what he's tried to do is he's tried to integrate the two things I've told you, which is really cool, which means you're thinking actively and you're thinking, how can I apply that? It turns out that this sort of structure here sort of really nicely maps onto this sort of testing approach, because it's really only when you get to the very end here that you have something you can test. Like, for example, suppose you're breaking it down, breaking it down, breaking it down, and you need to have a function that listens to the song and detects if it has love in it. And if it contains the word love, it subtracts 1 from the score. Okay. So that's, at some point you've got all the way down and you realise you need that one little function. And that seems much less daunting to write that than the whole big function. So you just go away and you write this little function and you're all happy and relaxed. How you test that then is you create some songs that have the word love in them a different number of times, including some words that have love in it 0 times. And you pump all those songs, and your test is, stick this song in, I expect to see the number 1 come out of that function. Stick this song in, I expect to see the number 0 come out of that function. Stick this, and you create some songs which have love in them. Like, so it's almost, you know, you trigger tricky cases. What about if words that sound like love? What about words that say love but it doesn't sound like love? You know, you think of all the crazy cases you can and you think of a test for each of those cases. Does that make sense? So yeah, you're exactly right. When you get to the end and you've got all these little obligations to discharge, as you discharge each one, write a test for it. And write a really pedantic test. See, the problem with testing, human nature again. When we write a test, do we want it to work or do we want it to fail? So everyone that said fail, you are good scientists, but you're also dishonest. Which reminds me of a story I heard about med students recently. Someone went to grad school and he had to sit a psychological test, some Australian scientist, to see what his personality profile was like to get into grad med school in the States. And he was called into the dean with the dean for an interview, and the interviewer said, have you got any questions for me? And he said, yeah, what did you learn about me from the personality tests? And he said, I learned that you lie more than average. And the guy said, oh. But you lie less than the average medical student. So computing students, you're up there somewhere too. Because yeah, when we do a test, we always want it to pass. If I've just built a really long fence and I've tensioned it and I've done it and I spent all day digging holes and putting the pots in, and then my employer says, now test this fence to make sure it's okay, I don't want to fix the fence up. I'm going, yeah, it's okay. It looks pretty safe. Does it wobble? No, it doesn't wobble. But if you really wanted to test it to make it fail, you'd bash against it, you'd throw cows against it, you'd do all sorts of things to make it fail. But it's human nature, because we're lazy, we don't want our tests to fail. So it's very hard to write tests. So yeah, we got to write ruthless tests, not easy tests. You've got to write the tests that will make it fail if it's wrong. And that's what being a good scientist is. You all know that. This theory of falsification. You come up with your theories and you try really hard to prove them wrong. It's only when you can't prove them wrong that you can say, oh, I have some confidence in the assertion I'm making, because I've tried to prove it wrong. Okay, it's called falsifiability. We try and do that in computing too. So that was test. Well, that was a good question. Thanks, Tom. Any more questions? Yes?
When you say test, you just mean compile it and run it? Or?
No, by test I don't mean compile it and run it. We actually write a little program to test it. And for the first assignment, that's a good question, thank you. For the first assignment, David, are you here? David, stand up so everyone can see you, David. Oh dear. David has written a tester for so they can see your front bit too. That's the side. Yeah, this is David. He's a really good helper. Thank you, David. Some of you are lucky and have him as a tutor. David's written an automatic tester for the first assignment that you can write test cases and it will run your program against all the test cases and tell you whether it's passing or failing. So his automated tester, for example, you could supply it with a whole lot of bits of music and a whole lot of scores, and it would one by one feed the music into your program and check it was giving it the right score for each one. If your assignment was to rate music. So yeah. I don't mean just compile it and hope it works. I mean actually have a systematic log test where you record the input and the output and check that it's all working exactly right. So that's a good question. Any more questions about testing? Hand up? Yeah.
Yeah, are we going through like the fine stuff that we missed in the first lecture? Or?
The fine stuff that we missed in the first lecture? It's Steve, isn't it? Steven. Yeah. What?
There was like a bullet point.
Oh yeah. Thanks very much. What I missed in the first lecture was, I'm just about to get to it when we go back to the coding here, in fact. Thank you for that. Any more questions about testing? Yes?
Have you tested the program which is responsible for the testing?
Have we tested the tester? Oh, Ipsos testodius. Who will test the tester? Has the tester been tested against itself?
Only briefly.
Yeah, but it should be, because, and he will. When you write a program, what a computer scientist does is they write the test first. So when you write any program, I'm not doing it in the lectures at the moment because we haven't done enough coding for you to see how to write tests. But from now on, in future weeks, starting after the break, every time I write a program, the first thing I do before I write the program is I will write a test for that program that tells us if that program is correct or not. And then I'll run the test, and the program, because I haven't written it yet, will fail. And then we'll write the program, and then I'll run the test, and it will pass, and we'll be so happy. So yeah, good question. The tester needs to be tested, and the tester needs to be tested. Yeah. And the tester. Okay, all right, all good questions. Any more? Yes?
Has anybody just created like a generic testing?
Yes. Has anyone created a generic testing program? Yes. When you're programming in Java next year, JUnit it's called. It's an awesome unit testing program. Unfortunately, there is no C unit. We have our own sort of way of doing testing here. Yeah. JUnit. Yeah. Automated testers are out there and all about all the place. Yeah. Okay. This program I've got at the moment is pretty good, but it contains a style problem. And the style problem is what we call a magic number. Can anyone see where there might be something called a magic number in this program? It's glowing magically. Why have I said dollars minus cents times 6? That doesn't make any sense. Unintentional. Why have I said that? It doesn't make any sense at all. How do you know it's 6 and not 5? How do you know I haven't made a mistake here? Let me not call them dollars and cents. Let me give them better. Let's call it length. Let's give them better names. And breadth. And it's not how I spell it. As long as I misspell it consistently, I'm okay. And breadth. And length and breadth. Now all the prompts are wrong. Oh. Length, breadth, cost. And this is some sort of estimation thing that the chef is using in his program.
You need to redefine as well.
Okay, the chef has to make a cake. Given the length and the breadth of the cake, what have I done? Oh, thank you very much. So given this enormous rectangular cake, given the length and the breadth of the cake, I want to work out what the cost is. And the cost is given by this formula. Is that formula correct? Well, it's looking right. It's got a length time breadth. That's got something to do with area. Intuitively, I'm looking at that. I'm thinking that sort of makes sense. Why is it times 6? We call that a magic number. You'll find in your programs, they'll get littered with magic numbers if you're not careful. The problem with the magic number is several problems. One, someone looking at your code doesn't know if you use the right magic number or not. Maybe 6 was right. Maybe I meant to type 60. If I give my program to you to check, how do you know if it should be 6 or 60? You've got no idea. Problem 2, this happened to me when I was writing programs for insurance companies. We assume someone's written a program to calculate the cost of an annuity. And they've assumed that inflation is 10%. They've also assumed that there's a 10% bonus payable every 5th year. I'm about to write the valuation program and someone says, uh-oh, inflation's gone up, it's 11%. Can you modify the program to make inflation 11%? I look at the program. It's full of magic numbers. It's got a whole lot of 10%ers in the program. Should I just change them all to 11%? No, why not? Some of them are probably for the bonus. Some of them might be for other things as well. When I look at 10%, I don't know its meaning. I just know the number. When I'm, as a human being looking at the program, I really want to know what the meaning is. So what I want to see in here is not 6. I want to see something like cost per square meter. Yeah? It's a big cake. Is that how you spell meter? Yes. Good. Thank you very much. Now that makes sense. Now I've given it a name, I've given it semantic content, and as someone looking at the program, I can look at it much nicer. I never want to see a magic number in your program because they're really hard to update, they're really hard to check if they're right. You'll end up changing some of them and not others when you need to change them, and it's all a big mess, and it contains no meaning to the reader. So now I've called it cost per square meter. I need to define cost per square meter, and see, let's just do that using something called hash define. Let's put it up the top of our program, under the hash include. Hash define cost per square meter is 6. Comment, it costs $6 a meter squared for cardboard. It's a cardboard cake. Okay, I put a little comment explaining it. I've defined that. Now the nice thing about this is suppose the cost of cardboard goes up. What do I have to change in the program? At the top. I don't have to go through the whole program looking for 6s everywhere, changing them and hoping I'm getting all the right 6s. I just change it at the top here and it changes everywhere. Now cardboard costs $7 per square meter. Or maybe I'm building it out of something else, some other material, and the cost is different. I just change it in one spot, the whole program magically works. So we get rid of our magic numbers, we hash define them. Now what does a hash define mean? It's an odd thing that's really only in C, and it shouldn't be there, and it's an ugly, disgusting thing, but it's the only way of doing it in C, so, well it was, so we're going to have to teach it to you. Hash define means before the program is compiled, remember hash include? I said before the program's compiled, the compiler sticks another file in. Anything beginning with a hash is an instruction to the compiler to fiddle around with your program before it compiles it. Hash include means sticks another file in. Hash define means rewrite. So it's going to globally go through my program, and wherever it sees cost per square meter, it's going to physically replace that with the number 7. And then it will compile the program. So it does a global search and replace. Does that make sense? And the compiler does it for me automatically. Convention is you put your hash defines at the top, You write them all in uppercase, so when people see it, they know it's not a variable, it's a hash define, and you separate the words with underscores. Yes?
What's the difference between using a variable and using hash define?
There's lots of differences between using a variable and a hash define. Thank you for asking that question. A hash define is done at compile time, before the compiler, in the pre-compilation phase. You cannot, it's just storing a constant, so you can't write to it. Yeah, it's just storing, the way we're using here is just storing a number, so it's read-only, which is how we define constants in our program. We don't want, if I had a variable there, people might change the value of that variable midway through the program. That'd be a disaster. This is a constant I never want to change. It happens at the top of the program, not even inside a function. There's something called scope that you'll see later on, which means variables don't live very long. They live inside a function, then when you leave the function, they die. Whereas this lives forever. So this lives globally everywhere in the program. It has all sorts of other advantages you'll see as we use it, but it is different to a variable. The main difference from your point of view at the moment is you can't assign to it. Yeah. Notice also, because it's doing a rewrite, we don't do this. Here's classic blunder number 1. And I thought we should have a classic blunders page. So why don't I set one up this week, and you guys can add to it too. Mistakes that programmers always make. Everyone makes this mistake. Oop, they don't make that mistake. They make this mistake. Why is that a mistake? Because everywhere the word cost per square metre appears in the program now, what's the compiler going to stick in? 7 semicolon. So down here where it appears, what's it going to look like? Oh, here it's going to be okay. It'll just replace it and it'll look like this. 7 semicolon semicolon, and that's just an empty line, yeah? No one cares about that. But what if I'd put cost per square metre at the beginning of the line? Oop. What's that? Oh, it should be length multiplied properly. Thank you very much. See, it makes much more sense. Dollars minus cents had no semantic meaning. We couldn't see it was wrong. Once you got length and breadth, straight away you know, oh, I expect to see those guys multiplying, not... Thank you to the one person who spotted that and said it.
A stylistic question.
Yes?
Should there be spaces after the scanfs as well as the printfs?
Yes, thank you very much. Stylistically, yes. What we're adopting in this course is one space after every function name. Thank you very much. Oh man, here's the problem. No, but it's important to get it exactly right. It doesn't matter what I do as long as I'm consistent in both spots. I really should have a protocol whether I use M or meter. I don't have that protocol. Okay, is everyone cool? This would be bad. 7 colon in here would mean cost is equal to 7, and the next line would begin star length star breadth. If we're lucky, that'll randomly mean something. If not, it'll be an error. No, actually, if we're lucky, that'll be an error. If we're unlucky, that'll randomly mean something, and the compiler won't notice that there's there, and the program won't do what we expect. All right, is everyone cool? You understand hash define? We're nearly at the end of the lecture, and I did want to show you about the assignment. Let me just check. Any questions about hash define? Yes?
Do you need to give that a type like a zero?
No, it doesn't have a type because it's not a variable. It literally gets rewritten in. So when I said down here, these are all very good questions. Cost equals cost per square metre. This will literally get replaced by the number 7. And when that gets assigned to cost here, it's being written to a variable. That variable needs to have a type because it's being stored there. So cost has to have been defined, but the number that I'm sticking into it's just a number. And the C will make all sorts of type assumptions. If it sees a 7 without a dot, it'll assume I'm sticking an int in there. If I put 7 point something, it'll make some other assumption. It makes a series of assumptions when it sees numbers about what type they are. You could force it to be a particular type, and we'll talk about that. If you hold that question for a couple of weeks, yeah, if you can hold on for that long, ask me how we could force that to be a particular type later on, and I'll show you how to do it. Yes?
If you hash define scanf, will that actually replace the variable?
Yes. If I hash define scanf, then everywhere in your program scanf appears, it'll change it. So you could do all sorts of crazy things. You could hash define scanf and call it get stuffed. And you could hash define printf and call it good grief. And you could then write your whole program just as like some sort of dialogue. And the hash defines would rewrite it into a program. In fact, there is a competition run called the obfuscated C competition. I'll get some obfuscated C. And that's people who spend their life trying to write programs that are so hacky that no one can ever read them. And it's a competition. And it gets judged for how impossible it is for other people to read it. And they normally start off with things like, hash define plus to minus. You know, they just redefine everything in the language. It's crazy. If anyone can find any of that, that would be a good thing to put up somewhere in the notes. Okay, any more questions about hash define? There are lots of good questions. Can you hash define, hash define? What am I going to say? No. Try and see. Try and see. I don't know. Try and see. Sounds fun idea. Okay. Good thinking. All right, now let's go back, because I do want to get to the assignment. It'd be terrible to get to the end of this lecture and not have done the assignment. Am I right in thinking we only have 7 minutes left? Yep. Is there less than 7 or more than 7? Bit more than 7. Okay, all right. All right, we've done a bit on functions. I've told you functions. All I've told you about functions so far is, because you've got a lab on them coming up, you say the type that it returns, the name of the function, and then inside brackets the things it's expecting. You have curly brackets, and everything between the opening curly bracket and the last curly bracket is the function. The last line of the function should be return something, and it should return something of the type that the function's expecting. Yep, you'll see. Well, this will be in the lab, so you'll fool around with it. There are functions that return nothing, and we'll also see those in the lab. So that's all I wanted to show you about functions. Now here are the notes. Mastering skills. I'm not going to do not a course on C. I'll do that next time. You will be going through this course and you will be learning how to program if you haven't programmed before. And if you have already programmed before, you'll be learning how to be a master programmer or just pushing your skills in one direction or another. You'll all have a reason for doing this course. Presumably, a lot of you are doing it because you're doing a computing degree, but then you've got a reason for doing a computing degree. You're all here presumably because you want to either be in a particular job or learn particular skills. It's not like school where you're here because you have to be here. Presumably you're here because you really want to learn some stuff. In particular, those that could have selected lower computing and selected higher computing instead, you've selected the challenge because you want to learn something. So you want to push your skills back. Just like my daughter who's learning the flute now. She really wants to play the flute. It's bloody hard to play the flute really well. It's bloody hard to be a really good programmer. It's bloody hard to do anything really well. So you're going to try and push yourselves and be as good as you can, but it's going to be hard. What's your biggest enemy, your biggest obstacle in achieving this goal? Not time itself. Yourself. Yeah, yourself. That's right. Your biggest obstacle is yourself. Her biggest obstacle when she's learning the flute is she's going to give up. She's going to get bored and stop. She really would love to be like 16. She's only 10 or something at the moment. She'd love to be 16 and be able to play fantastic flute music. And when she's sad, play something sad. And when she's joyous, play joyous, uplifting stuff. She'd love to be able to do that. But there's a path of pain between here and there. Most people that try and learn a musical instrument give up and drop out. And I was sitting next to a lady who taught primary school students musical instruments. She was a prize-winning lady. She was just about to get a prize for it. And I was whispering to her, hey, tell me all your secrets. How do you motivate the kids to learn musical instruments? She said, most kids in primary school, because we're whispering because she's about to be called to stand up and get a big prize. Most kids in primary school, they start learning instruments, they give up. I'm saying, what do you do? How do you stop them giving up? Because I wished I hadn't given up. I wished I could play the piano. I gave up. I'm really cross now. Me 10. Me, whatever, 40 is angry at me 10. Okay. Me 10's gone. It's too late. I said, what's the secret? How do you do it? She said, the secret is... Now, what do you think it is?
Foursome.
That's certainly what I've tried as a parent, and my parents tried on me. How successful is the foursome strategy, do you think? Yeah, I would say pretty close to 0, unless the child has no will and you've completely sapped all their independence from the age of 5 and you've brainwashed them into being a puppy or something like that. Essentially, unless you're a really domineering parent and you've crushed the soul of your child, forcing isn't going to do anything. How are you going to make someone learn the piano? How are you going to make them learn a musical instrument? She whispered the secret to me just as she was standing up. Make them want to learn it. She said, it's just got to be fun. They'll get there eventually. The worst thing is them giving up. So you just sit down and have fun. Make the piano part of your everyday life. Have a family sing a long time. When they're playing something, anything, praise them and show them how good it is. Get them to associate it with a good time. Show them the excellence that they can do rather than constantly berating them for the small little bit they haven't got right. If it's fun and they want to do it, the problem will solve itself out. They might leave it for a couple of years, but they won't remember they hate it, and they'll drift back to it when they're older. And music never leaves you. She said, you just can only stuff it up if you make it a chore and horrible. Make it fun. And then she stood up to get her prize because she's done all these amazing things around Australia helping people learn how to play musical instruments. Now, it's the same with programming, I realised. You've got to go through a lot of pain, but along the way we've got to make sure that you actually get bits of pleasure. I woke up at the beginning of this year and thought, oh no, I've been working so hard the last couple of years. I've stopped jogging. I've stopped, I used to do like lots of bushwalking and climbing. I used to be really careful what I ate, and I thought, oh man, since my little baby was born a couple of years ago, I haven't gone on jogs, I don't do anything, I get puffed walking up the stairs, I'm getting all flabby, I eat crap food. Oh man, I've got to get in shape. Now this is probably the biggest vow made by any Australian ever. You know, all Australians make this vow all the time. Why? So I was speaking to a friend of mine who's a health scientist. I said, why do people, people when they want to get fit, what happens? How come most people sort of get fit a little bit, then they fall away? She said, well, most people don't make it fun. So what happens is they try really hard and they set themselves up for a program that doesn't give them any rewards or enjoyments. They get to some point and then they hate it and they give it up. She said, the only way you're going to get fit is, well, you tell me, how am I going to get fit? Make it fun. I've got to work out activities that fit into my everyday life that I enjoy doing that help me achieve my goal. So I love walking and planning my lectures and thinking. So I should go for more walks. I should make sure there's only yummy food in the house that's healthy. Yeah, then I get yummy food and I get healthy. I should constantly give myself praise and motivation for my successes. And I shouldn't be hard on and I just worked out this long list of stuff. And I might even put it in the lab this week. You guys think of tips for helping me become fit and healthy. My plan is by the end of this course, I'm going to be fit and healthy again. Your plan is by the end of this course, you're going to be an elite programmer. It's going to be lots of work, so you're going to have to manage your own personality and motivation to make sure you stick with it. And my advice to you is the same as her advice to me and the piano teacher's advice to me, which is do a bit of practice all the time, practice every week, a couple of hours all the time, never stop. Now, have we run out of time? Well, let me tell you what the assignment is. It's just here. Shh, shh, shh. The assignment's about software piracy. Software, as you know from our computer chip, is just a whole lot of numbers. And the biggest pirates in the world were the Vikings. Yeah. So this assignment is all about Viking numbers. All right. Ask Bjorn. You have to write a program. Hey, why can't I get the image? Oh, it's really slow. Okay. Oh, now I've gone too far. It's going to load. I'm going to type in a number, and this is going to tell me how a Viking would have pronounced that number. Viking didn't have digits. Whenever they wanted to write a number down, they had to actually write it down. There's scant research on how the Vikings spoke and how their number system worked. I've had to make up a few, and I haven't exactly obeyed all the normal rules. So you'll never be able to look up on the internet exactly how the Vikings did it. Your only real clue is this program. 56, what's the Ketchup thing? U, D, M, F, N, G. F, N, Q. Thank you very much. Far North Queensland. Submit. They would have said, Fum Tigger Oxex. Your first assignment is writing a program that reads in a number using scanf and prints out using printf what a Viking would have said. You're going to have to break it into bits. How are you going to start working on this? What was the easy bit you're going to do?
First figure out a lot of numbers.
Just do some of the numbers. Yeah, just try and get it working for numbers under 10. Then try and get it working for numbers under 100. Then try, break it into bits. Okay, go. I'll see you on Wednesday.